Welcome back everyone. In this lecture, we will see the structure theorem for finite abelian groups. Okay, let us do some warm up before stating the main results. So, recall the following isomorphisms. So, if we have two cyclic groups, let's say order n and m, so z modulo nz cross z modulo mz, then we have proved that this is isomorphic to z modulo nmz if the GCD of n and m is 1. Okay. So, whenever the orders of these two groups are relatively prime, then the product of these two cyclic groups, they are again cyclic group. Okay. For example, if you take z modulo 2z cross z modulo 3z, so then we get it is isomorphic to z modulo 6z naturally. Okay. So, now I will leave it as exercise. Okay. Now, this can be generalized further for any given relatively prime numbers. Okay. Suppose if you have some m1 etc. mk, so these are all natural numbers such that the GCD of m1 etc. mk, if this is 1, okay, let us say, so this is given. So, then we can actually prove that z modulo m1z cross etc. cross z modulo mkz is naturally isomorphic to z modulo the product. So, this is indeed a consequence of Chinese remainder theorem. Okay. This is something we have already seen, but I am restating it, okay, for our convenience. Okay. Now, this tells actually if you are interested in looking at this product of cyclic groups. So, under some condition the product of cyclic groups actually becomes again cyclic group. Okay. So, now let us try to understand what happens in some smaller order which we already understand. Okay. If we take for example order 4, okay, then actually we proved that if G is abelian group, okay, then G must be, okay, any group of order 4 is abelian, that is something we have already proved. But I also actually gave you this as exercise. So, any group of order 4, either it is isomorphic to G modulo 4z or G modulo 2z cross G modulo 2z. Okay, these are all the only order 4 abelian groups are there. So, here you can see that, so this group if we take z modulo 2z cross z modulo 3z, all of its elements they have actually order 2. Okay. But here we have order 4 element. Okay. So, if we go to order 6, then what happens? You have z modulo 6z. You are tempted to divide 6 equal to 2 into 3, but 2 and 3 are relatively prime. That forces that this z modulo 6z is isomorphic to z modulo 2z cross z modulo 3z. Because if you are in a group like this z modulo 2z cross z modulo 3z, so you have a element of order 2, okay, coming from first component, okay, and then you have element of order 3 coming from the second component. Because they commute and the orders are relatively prime, the product will have order 6. So, that is why, so this z modulo 6z actually becomes isomorphic to this. Okay. So, this phenomena is actually true in general for any group. Okay. So, this is something I already proved, I am just recalling it. You have a group, let us say G, and A and B both are elements of G such that AB commutes. Okay. So, now look at order of A and then order of B. So, both are, let us say, finite and the GCD is 1. Okay. So, both are finite and the GCD of this n and m, this is actually 1. So if you have such situation, then we know what will be the order of AB. The order of AB is going to be the product of the orders of the respective elements. So this is something we already proved. Okay, this is very important fact. So now using this, you can see that if you have some groups like this, okay, Z modulo M1 Z cross etc. Z modulo MK Z, where M1, M2 etc. they are all relatively prime. So then the first so there will be order M1, order of M some element which has order M1 from the first component and M2 from the second component and so on. So then if you look at their product, then that will have definitely order which is product of MIs. So that is why this particular group has element of order product Mi. So that means this must be cyclic. So that's what we get. So because it's a cyclic group of order product of Mi, so it must be isomorphic to Z modulo product Mi Z. Okay. So now if you are in a finite abelian group, okay, this property that we have written here, this AB and AB equal to BA, that's AB commutes. So that actually automatically true for all elements of this finite abelian group. So that's why we have this following result. Okay, so I will state it as lemma. So it's a very crucial result in order to understand the structure theorem of finite abelian group. What it says, you start with the finite abelian group, and then say that the order of the group is n. Okay. So now what we can do, we can look at all possible orders of the elements of G. So let's look at order of X in G. So because G is finite, these numbers are finite, so one can talk about the maximum. So let's say the maximum is D. Okay. So then what one can prove, so then if this is the given condition, then order of G must divide D for all G in G. Okay. So this is a very important fact about finite abelian groups. So this maximum order of all elements, so that is called exponent of this group G. Okay, this is called the exponent of this group G. Okay, so sometimes it is also denoted by E of G, the exponent. So what we are saying, the exponent is divisible by all the orders of the elements. Okay, so very crucial fact. So let us prove this. So what we do, so because this exponent is maximum of order of X for all X in G, so there will be some A in G such that the order of A will be equal to this exponent D. Okay, so choose A in G such that order of A equal to D. So let us say fix this G in G. So we want to prove that order of G actually divides D. Okay, so let us say it is not true. Okay, then by contradiction you have a G in G such that order of G actually doesn't divide D. Okay, let's call this order of G M. Okay, so M actually doesn't divide D. So now this M is actually not dividing D. You can see that if you look at the prime factorization of both D and M, okay, you will have some prime of prime factorization P of this M such that P power R divides M and P power, let's say, S divides D, but the exponent, this R is greater than S. Okay. So just look at prime factorization of both M and D, because M doesn't divide D. So at least for one prime divisor of M, okay, so we will have actually the exponent, that P power R that divides M, that R is should be strictly greater than the exponent P power S that divides D. Okay, this is, let's say, largest power such that p power s divides t. So note that this s can be very well 0. So that we don't really care. Okay. So this is the largest power of p. Okay, there exists a prime p such that okay R and S satisfying this property. R and S such that they satisfy this property. Okay, so now let us look at what happens to some specific elements. So recall, so order of some x power k is nothing but order of x divided by the GCD of k comma order of x. This is something we have proved. In particularly, if you take k being the divisor of order of x, then order of x power k is going to be order of x divided by k, because the GCD of k and order of x is going to be k. So in particularly, what will happen? Order of a power. So let's look at this p power s. Okay. So then what it is going to be? So order of a we denoted it by d. Okay. So order of p power s is going to be d divided by the order of this okay, the p power s is dividing d. So this is going to be just divided by p power s. So what will happen to order of this g power? Let's say g power p power r. So now p power r divides m. M is order of g. So in particularly, so you get exactly. So okay, maybe we will look at m divided by p power r. Okay, then it is going to be exactly m divided by p power r. So which will give you p power r. Okay, so now look at this element, order of this a power p power s times g power m divided by p power r. Okay, so what it is going to be? So note that this p power r and d divided by p power s, they must be relatively prime, because p power s is the largest power of p that divides d. Okay, this is here. So p power s is the largest power. So that means once you have divided this d by p power s, there is no p factor there. Okay, so that means p power r d p power s should be relatively prime. So now using that, you can see that the product, this one, okay. Okay, so I have put d as the exponent. So this is the exponent of g. So I need to get something bigger than d. So maybe I should actually look at. So I should look at this d. Okay, so let's see. So this is m divided by p power r. So then this is going to be, so order of a power p power s times order of g power m divided by p power r. So which is going to be what? Which is exactly equal to, so d divided by p power s times p power r. So this is order of a p power s times g power m divided by p power r is equal to this. But this is exactly d into p power r minus s. But note that r minus s is greater than or equal to 1, because r and s has the comparison. R is not equal to s and r is strictly greater than s. So that means this number, whatever it is, d p r minus s is strictly greater than d. So you have produced some element a p power s times g m divided by p power r inside G, whose order is strictly greater than d. That is actually contradiction, because we have started with d being the exponent of G. So, that is the max of all order. Okay. So, that simply says by actually playing around with these order properties, you can produce some element in G which has more order, if order of G does not divide this D. So, this proves that for any G in G, order of G actually divides this exponent of G. So, this is what we have proved. So, this is a very crucial observation. Okay. So, now one can use this observation to prove the structure theorem. Okay. So, let me just state one version of the theorem, okay, and I will prove that. So, we will also actually prove another version. So, there is one version uses what is called elementary divisors, the other version actually uses what is called invariant factors. Okay, now I will state the version that uses invariant factors. So, here is the structure theorem using invariant factors. Using invariant factors. So, I will explain in a minute, okay, using some examples what we mean by this. Okay. First, let us actually see the statement. So, we start with a finite abelian group. Okay. Let G be a finite abelian group, okay, with let us say order of G is n. So, then what one can prove, then there exist unique tuples, okay, H1 etc. HR. So, satisfying the following property, satisfying, okay, the very first property, all these HIs, they are all cyclic groups for all I from 1 to R. And the second thing is G is actually isomorphic to the direct product of these cyclic groups H1 cross, H2 cross etc. HR. And the third property, this is most important property, that is what makes these groups actually unique, satisfying this 1 and 2. So, what this important property, it is actually gives some restriction on the order of HIs. So, the order of HI plus 1 must divide order of HI for all I from 1 to R minus 1. Okay. So, this is actually a version of structure theorem of finite abelian groups using invariant factors. So, these factors that are appears in this factorization of G into product of cyclic groups. So, they are called actually invariant factors of G. So, note that the uniqueness actually tells these groups H1 etc. HR, they are uniquely determined by G. Okay. So, now since actually we are going to work with finite abelian groups, so one can actually write down everything in using the additive notation, there is no issue. So, some books actually, so here's the remark. So, some books uses additive notation for G. So, G plus is used for abelian group, and in particularly this direct product of this abelian groups written as direct sum of groups. So, in this case we also write G is isomorphic to H1 direct sum etc. direct sum HR, because all the elements commute. So, it makes sense to write in this direct sum notation. So, this notation used by some books. Okay. So, if we think about it, this statement actually possesses lots of information about the group G. Okay, let us try to understand what informations that we get from this statement. First of all, it says that any finite abelian group is actually isomorphic to direct product of cyclic groups. Okay, that is the first statement. So now, if we look at the order of G, the order of G should be the product of order of this Hi. Okay, if we denote Mi by this order of Hi, so you can see that the following things should be satisfied. So the order of G, that is supposed to be the product of all these Mi's, that is the first thing. So that is clear from the second statement of the theorem. So then you can see that the third statement can be rewritten as Mi plus 1 divides Mi. So that means Mr divides Mr minus 1 and Mr minus 1 divides Mr minus 2 and so on, and M2 divides M1. So these are all the two important properties of Mi's that can be stated this way. So some books uses this notation to say that Mi plus 1 divides Mi for all I from 1 to r minus 1. So now let's try to understand, okay, what will happen to the exponent of G. Okay, so it is easy to see from the statement second, the exponent of G must be the order of H1. Okay, so H1 is actually the largest cyclic subgroup of G. Okay, so that means, okay, the order of this exponent, maybe I will leave it as exercise. Okay, so verify that the exponent of G, which is the maximum order of all elements of G, is going to be order of H1. So note that each Hi, they are all cyclic subgroups. So in particularly there will be some Xi, okay, there exist Xi from this G such that, okay, this order of Xi will be exactly Mi. Okay. Now if you think about it, order of X1 is M1. Okay. So now if you take some typical element in G and then ask what will be the order, then what it will be. So let's take some typical element, call it G in capital G. Okay. So then G will be, because G is isomorphic to H1 cross etc cross HR. Okay. So you can identify G with some elements like this, H1 etc HR, where Hi comes from capital Hi. Note that Hi is nothing but cyclic group which has order Mi. So it is isomorphic to Z modulo Mi Z. Okay. So then what will be the order of G? The order of G is going to be LCM of order of this Hi, because all these Hi's commutes. Okay, you can think Hi as, so this particular element identity etc identity Hi, identity etc identity. Okay, so this can be identified inside that ith component. So Hi sits naturally inside this H1 cross etc HR at the ith component. Using that, you can see that this order of G is going to be the LCM of all these numbers 1 to R, because they are all commuting. So in particularly order of G will be just LCM of this. But note that order of Hi is actually divides Mi, and Mi satisfies this property, Mi I plus 1 divides Mi. So that means what should be the LCM? LCM is the least common multiple. So you can see that order of Hi is actually dividing M1 for all I from 1 to R. So that means the LCM also will be dividing M1. Okay, so that means order of G divides M1. So that says that the largest order in this direct product H1 cross etc HR must be the order of H1. Okay, so that means the exponent of G must be this this particular group order. Okay, So this actually motivates us to look for some very particular subgroup of G, okay, and that actually plays the role of H1, okay. So we will actually kind of try to understand this theorem first, and then using all the observation that we are making now, we will prove the theorem. So in a way, the exponent of G is captured by the order of this H1. That's what we saw. So now you can see that if you take any finite abelian group, okay, so then we are saying that that must be isomorphic to direct product of cyclic groups, okay, that you can get it as corollary of this. But if you ask whether if you know this information, given a cyclic group that is actually product of direct product of cyclic groups will imply this particular version of G, okay, that also actually can be worked out, not a problem. Okay, all these statements I will be proving in follow up classes. Okay, so and I will also prove the another version of this structure theorem using using what is called elementary devices. Okay, and we will try to understand how to go from this one version that uses the elementary devices and the another version that uses this invariant factors. So we will see that how to go from one to another using some examples and so on. Okay, I will stop here and then I will continue with the proof of this in the next class. Thank you.